All right, welcome to episode 16. We finally hit double digits. In this episode, we will introduce the idea of interrupts and present some background on what they're for and how they work and how we're going to use them in our 6809 system. We'll go through some initial hardware modifications that are going to be necessary to allow the system to support interrupts. We'll test the hardware with those new modifications, and then we'll wrap up by explaining what we will need to do to actually add an interrupt controller to the system and modify the monitor program to take advantage of it. All right, let's get started. Before we delve into the hardware and software changes required for supporting interrupts in the 6809 system, let's discuss some background. First, let's talk about what interrupts actually are. Interrupts are a hardware and software mechanism which allow the system to promptly attend to hardware devices which require attention. Some examples of hardware devices requiring attention are: a timer device has signaled that a timer event has occurred, a UART received some data, a key was pressed or released, and the keyboard controller has data available. When a hardware device requires attention, it notifies the CPU by asserting the CPU's IRQ interrupt request input. Because many devices may generate interrupts, a system will often require interrupt controller hardware to allow many devices to share the same interrupt request input. We will discuss an interrupt controller design for our 6809 system later in the video. When the CPU detects that its interrupt request input has been asserted, it waits until the current instruction has completed its execution and then pushes the current program counter value and status flags onto the stack, and then jumps to the interrupt handler routine. The interrupt handler routine is responsible for responding to the hardware condition which caused the interrupt. For example, if the interrupt occurred because data had become available, the interrupt routine could read the data from the device and place it into a buffer in memory. Once the interrupt handler is completed, it will execute a return from interrupt instruction, which restores the original program counter and status flag values, allowing the CPU to transparently resume whatever code it was executing when the interrupt occurred. So why are interrupts useful? There are many reasons, but here are two important ones. First, interrupts allow background tasks to be implemented without the direct involvement of the currently executing program. Some examples of background tasks are I/O, timer event processing, and other housekeeping tasks. Because interrupts are handled automatically, they simplify application design by allowing a clean separation of program logic and interfacing with the underlying hardware. Second, interrupts are the core mechanism enabling multitasking. For example, a system supporting a periodic timer interrupt could use the timer interrupt to switch between multiple concurrent tasks. However, even though interrupts are useful for multitasking, they can be just as useful for single applications. Next, let's examine the sequence of events when an interrupt is handled. First, an event requiring attention occurs. As an example, let's say that a byte of data has arrived at a UART device. The device will assert the CPU's IRQ input, notifying it that a device requires attention. The CPU will then begin execution of the interrupt handler routine. The interrupt routine must determine which device requires attention and access the device to resolve the situation requiring attention. In the case of a UART with data available, the interrupt routine should transfer data from the UART to a memory buffer. It is important that the interrupt routine completely resolve the situation that triggered the interrupt so that the hardware device deasserts the CPU's IRQ input. Otherwise, the interrupt handler routine will be executed over and over again. Once the interrupt routine has resolved the condition which generated the interrupt, the hardware device will deassert the IRQ signal. The interrupt handler will return once it is completed. Assuming that IRQ has been deasserted, normal execution will resume. One important detail of hardware interrupts on the 6809 is that there are three inputs used to detect interrupt requests: IRQ, FIRQ, and NMI. NMI is the non-maskable interrupt and can be used to notify the CPU of very high priority conditions. We won't be using it in our design. The IRQ input is for normal hardware interrupts. One very convenient aspect of IRQ is that the CPU will automatically save and restore the contents of all hardware registers when dispatching to and returning from the interrupt handler routine. This means that the programmer can freely use all of the 6809 hardware registers without causing problems for the program code that was running at the time the interrupt occurred. The FIRQ input is the fast interrupt request input. The CPU will save and restore only the program counter and condition code register when it detects that FIRQ is asserted. This means that the programmer must be careful to manually save and restore any CPU registers used in handling the interrupt. For our design, we'll be using the IRQ input since it's simpler from a software perspective. There are two complications that we will need to consider. The first complication is that if the system will support multiple devices generating hardware interrupt requests, but the CPU has only one or a small number of IRQ inputs, logic will be needed to combine the per-device IRQ signals into a single IRQ signal that is asserted if any hardware device requires attention. In addition, if a single CPU IRQ input is shared between multiple devices, it is helpful to have additional logic that helps the CPU determine which device generated the interrupt in order to efficiently resolve the condition which triggered the interrupt. The interrupt controller logic could be a dedicated IC or could be constructed using discrete logic. The interrupt controller for the 6809 system will be constructed from discrete logic. The second complication is that some devices generate edge-triggered interrupt request signals. Most devices generate a level-triggered interrupt request signal, meaning that the device asserts an interrupt request until the condition it is reporting is resolved. An edge-triggered interrupt request consists of a single pulse occurring at the time of the request. If the CPU does not directly support handling of edge-triggered interrupts, and the 6809 does not, then some form of sequential logic such as a flip-flop is needed to capture the pulse and generate a level-triggered interrupt request. The interrupt controller for the 6809 system will use two D-type flip-flops to allow edge-triggered interrupts to be handled. Next, let's talk about some hardware changes that we'll need to make in order to get the system ready to support interrupts. So here is the original version of the schematic for the core module, and what we can see is that pins 2 through 4 on the CPU, which are the ones that allow the CPU to detect an external interrupt, are all tied directly to VCC, the positive supply voltage. So essentially, they are all held constantly high, meaning that the CPU never registers an external interrupt and dispatches to an interrupt handler. So in the revised version of the circuit, these same inputs, 2 through 4, are now tied high using pull-up resistors. And what essentially this allows us to do is actively drive those signals. So for example, here we can see that this IRQ signal, that is going to be generated by the interrupt controller. And when the interrupt controller detects that one of the external interrupts has been asserted, it will drive this IRQ signal low, which in turn will drive the IRQ input on the CPU low and will cause the CPU to vector to the IRQ handler. And so essentially anytime hardware interrupt occurs, the IRQ handler will be executed. However, if these signals aren't actively driven, that's perfectly fine because the pull-up resistors will keep them high in the steady state. All right, so here is the core module, and you can see these 3 pull-up resistors right here on pins 2 through 4. And the IRQ pin, which is pin 2, is now tied directly to one of the signals on the back plane, and that will allow the interrupt controller module to pull this input low. Here is the schematic for the original version of the peripheral module, and what we can see is that the output for Unit 1 on the 82C54 timer counter doesn't actually go anywhere, and what we will do is, on the revised version of the schematic, is send that output to a signal on the back plane. And essentially what we are going to do is configure that unit of the timer counter to generate a periodic timer pulse. And what we will need to do when we design the interrupt controller is allow the interrupt controller to detect that pulse. Essentially, we need an edge trigger detection mechanism in the interrupt controller such that the edge of that interrupt signal can be converted into a level triggered interrupt so that the IRQ signal can be generated properly to allow the CPU to vector to the hardware interrupt handler when a timer interrupt occurs. And we'll talk more about that when we discuss the design of the interrupt controller. All right, so here is the peripheral module, and pin 13 on the 82C54 is the output for Unit 1. And if we look on the back, essentially what we have here is a wire that goes from that pin onto an appropriate currently unused backplane signal, and that will take that timer interrupt pulse
and make it available to the interrupt controller. All right, so as you do hardware development, I think it's a good idea to have a healthy sense of paranoia that basically anytime you make changes to the hardware, you test to make sure that it is still working after you've made the changes. So I have the monitor program running here. I've uploaded my count test program. Let's execute that, and good. So we see the counts going up. So the circuit does appear to still be functional after making our changes. So that means that we should be clear to now work on the design and implementation of the interrupt controller. To completely integrate interrupts into the system is going to require the creation of a new hardware module, the interrupt controller module. I'm not going to go through the detailed design in this video. I would like to give you sort of a preview of what's going to be involved. There will be a couple of hardware registers associated with the interrupt controller, and so we need the memory read, memory write signals, and a chip select. There will be inputs for the various hardware devices to signal that they want to generate an interrupt. So here's our timer IRQ signal, which is an edge-triggered interrupt. And then because we have some flip-flops that we're using to translate the edge-triggered interrupt signals into level-triggered, we need clear signals for those flip-flops. So if we go into the schematic here, this is the interrupt controller hardware. Yeah, I'm not going to really talk about it too much now. This section of the schematic is where we combine all of the various interrupt signals into a single IRQ signal that can be sent to the CPU. So that's how essentially we're supporting many hardware IRQ inputs that feed into a single CPU IRQ input. But we'll go through the full design in the next video.
All right, well, hopefully this video gave you an idea of what we're trying to accomplish in adding support for interrupts to our 6809 system and how we're going to go about building the hardware. So in the next video, I will go through the detailed design of the interrupt controller hardware. We'll build the actual circuit for the interrupt controller on breadboards and try to get it working with the system. We'll add software support to the monitor program so that it can detect interrupts and do something interesting. And we'll put this together in part 2. So hope to see you then.